This is Mrs. O'Neill for Chapter 7, Section 4, Ionization Energy. At the end of the section, hopefully you'll understand what ionization energy is and how the trends appear on the periodic table and how it's related to effective nuclear charge and the radius of atoms. Again, I suggest you to pause, fill in the blanks, and then play to hear my words. Ionization energy is the minimum amount of energy required to remove an electron from an atom or an ion. The big thing here is gas. Ooh, gaseous atoms. I don't know about you, but when I think of sodium, I think of sodium solid. So I'm not thinking about those electrons being removed in the gas phase. And also in the ion, right? Sodium as an ion, I think of salt dissolved in water, and then that salt turns into Na+. Again, that's an aqueous. That is not a gas. So one thing we need to understand or wrap our head around when we're talking about ionization energy is we're talking about the amount of energy to remove that electron from that gas atom or that gas ion, something that we're not used to seeing or hearing. So how many ionization energies are there? Well, depending on how many electrons there are. So if you have sodium, let's say, has 11 electrons, that means it has 11 ionization energies, the amount of energy needed to remove each and every one of those 11 electrons. So the first ionization energy, obviously, is how much energy is needed to remove that first electron from the neutral atom. But the second ionization energy is going to be the amount of energy to remove the second electron from that ion. So if we remove that first electron, obviously now it becomes an ion. And how much energy is needed to remove the second one from the ion, okay? The higher the ionization energy, the more difficult it is to remove that electron. We'll talk about that in more detail, but that should make sense. The more electrons we're removing, the more energy it's going to be needed. So here is an example of sodium, okay, going back to sodium, but it's in the gas. Notice these are all in the gas states, okay? It is not in the solid state that you're used to. So sodium gas going to that sodium plus ion takes so much energy. Now, how about the second ionization energy? Going from the Na plus, going to Na+2, which we rarely see, would this take more or less energy? Hopefully you guessed more, and it's going to take a heck of a lot more. Why? Well, going from sodium to sodium plus, again, we're used to seeing that because it has 1 valence electrons. It's used to giving up that 1 valence electrons. No problem, because it's a metal. But sodium +1 to sodium +2, now we're talking about that core electron or the inside electrons that are on the inside energy levels. It's going to take a heck of a lot more energy to remove that electron, and then so on and so on and so on. So here's a chart of the ionization energies in kilojoules, and let's look at beryllium for an example. So beryllium is in group 2, so it has 2 valence electrons. So that first valence electron, 900 kilojoules of energy, not a problem. And then the second valence electron takes a little bit more energy, 1700, but those are still valence electrons. Now, why the difference in energy? Again, because of that nuclear charge, or that effective nuclear charge. Because, again, beryllium is going to have 1, 2, 3, 4 protons, okay? So no matter what, it has 4 protons, which means it has 4 electrons. So when the first electron is removed, it still has 4 protons, but now it only has 3 electrons. So the attraction between those positive protons and the 3 now negative electrons is going to be stronger, so that's why it's going to take more energy. Now, once you remove those valence electrons, boom, look at this. It jumps up to 15,000. We're going less than 2,000 to 15,000 in energy to remove that third electron. Why? Because that third electron is the core electron, and now that third, fourth electron is really, really close to those positive protons, okay? So that attraction is really strong. So if you look at boron, again, boron has 3 valence electrons. It has 5 protons, 5 electrons, so those first 3 are valence. So again, it's going to take a little bit more energy each time because of that attraction between those positive protons and negative electrons. But then when you jump to that fourth or that core, that first core electron, you're going from less than 4,000 to 25,000 kilojoules of energy. That's a huge jump, okay? So hopefully you understand that. And again, to just show the valence versus core and the amount of energy needed. So here we have sodium with 500 kilojoules of energy to remove that first valence electron, but then going to that second core electron, or that second ionization energy, you're jumping up to 4,500. So that's a big jump and a big difference. So it is called successive ionization energies because it always talks about removing those electrons in order. So first valence electron, second valence electron if there is one, third core electron, and so on. So it's just the amount of electrons there are. Like sodium would have 11 total electrons, so there would be 11 ionization energies. So the amount of energy for the first, the second, the third, and so on. Okay, so why does it take more energy? Hopefully you understand, because as those electrons are closer to the nucleus, it's going to take more energy to remove it because the attraction between those protons and electrons. So what's the trend? Going down, that should make sense. Going down the group, it decreases. It doesn't take as much energy to remove those electrons because those valence electrons are going farther and farther away from the nucleus. And the next slide shows you this trend and the periodic table. I could explain a little bit more detail. As we go across a period, the strength increases, because think about this, you're going from metal to a non-metal. Metals don't mind giving up their electrons, so it's easy to remove, where your non-metals tend to gain electrons. So since they tend to gain electrons, it's going to take much more energy to remove those electrons. And you can read this information about that in the S and the P block. There's a huge increase, where in the transition metals, there's not so much. So if we look at the periodic table, again, we're looking over here at the metals. These tend to become cations because they have low valence electrons, right? A low amount of valence electrons. So like we talked about lithium and sodium, it's going to be very easy to give them up. They become cations. And we want to remember, hydrogen has 1 energy level, lithium has 2. Going all the way down here to cesium has 6 energy levels, and that 1 valence electrons all the way on that 6th energy level. So it's going to be real easy to give that up. Versus fluorine as your nonmetals. Now fluorine is a very small atom to begin with, right? Because we have the atomic radius as we go across gets smaller because of that effective nuclear charge, and the attraction between those protons and electrons gets stronger. So now it has 7 valence electrons, and it's a heck of a lot easier to gain electrons than to remove them. And so for that reason, it has a high ionization energy. So a lot of these trends, I actually like to think of them as a diagonal. So on your bottom left is going to have less ionization energy, and your top right, except for the noble gases. Now remember, those noble gases are stable. They're not going to let anybody take their electrons away. So we just kind of don't really even talk about them when we talk about ionization energy. But fluorine then would have the highest ionization energy. So when we talk about configurations of ions, we talk about how they are going to be removed or added to that last orbital. So if we look at a cation, that 3s1 is actually going to be removed. So we have Na, we have those 11 electrons, we have that 1 valence electron, but when it becomes an ion, notice there's no more 3s1. That orbital and that whole energy level in this case has been removed. Again, for cations, we have CO going to CO plus 2. That whole 4s2 electrons are going to be removed. Now, if we have more electrons being removed, then it's going to take from the 3d orbital. And so one of the 3d 1 electron orbital is going to be removed. So if we look at it the other way, right, so it's always added to anything that's partially filled or empty. So if we look at chlorine, again, we have chlorine here with a neutral atom, but we have that 3p orbital that needs to be filled. So in the Cl-1 ion, that addition of the electron is going to be in that 3p. It should have, 3p1 is added. One of the electrons is added to the 3p1, making it 3p6. So hopefully that didn't blow up your brain too much.